Good afternoon, everyone. Can I ask you to take your seats, please? Good afternoon, everyone. Thank you for staying for session 4, which I think is going to answer a lot of your unanswered questions about linked open data and the exchange of information. We're in a very fortunate position at the Wildenstein-Plattner Institute, not only because we were given the gift of archives from the Wildenstein Institute, but because we also benefit from the brain trust of the Hasso-Plattner Institute. And what we have learned as art historians, the importance of exchange of information and the cross-pollination of ideas is very important, I think, laterally, but now we're going to expand the conversation, if I may, longitudinally, and we're going to involve the tech developments that are enabling digital art history. One of the biggest challenges that we have found at the WPI is merging the languages of art history and IT. And both have a lot to learn from each other, but when we are open to these exchanges, we really benefit on both sides. I think what you're about to hear is going to open up a new world for what is possible in digital art history, particularly if we as art historians and researchers and scholars and museum professionals are open to listening and having a dialogue about technology and artificial intelligence. And of course, it might seem a little bit daunting at first, particularly for those of us that, like myself, that don't have a background in data science, but the benefits are enormous and we only stand to gain from them. So with that, I'd like to introduce our first speaker of our last session of the day, which is entitled Technological Developments, Accessibility and Utility Through Digitization. Our first speaker is Professor Dr. Christoph Meinl, the President and CEO of the Hasso-Plattner Institute, HPI, University of Potsdam, Germany. Christoph Meinl is President and CEO of HPI for IT Systems Engineering and Professor of Internet Technologies and Systems. He is a visiting professor at the School of Computer Science of the Technical University of Beijing and a research fellow of the S&T Security and Trust Interdisciplinary Center of the Luxembourg University. Under his leadership, the HPI School of Design Thinking in Potsdam opened in 2007. He is one of the major advocates of the design thinking method in Europe and has been teaching at the HPI School of Design Thinking since the beginning. A mathematician by training, Christoph Meinl received his graduate degree, doctorate, and postdoctoral degree from Humboldt University of Berlin. He is the author or co-author of 10 textbooks and monographs and has published more than 350 articles in internationally recognized peer-reviewed journals. Please welcome Dr. Meinl. Thank you.
Thank you, Liz, and it's a great honor to come into contact in the direction with you, because I had an experience already since we have in the Plattner family a young sister, the Barberini Museum, that there is beside of IT and digital engineering, there is another world. Sometimes the worlds are very distributed, the world of engineers, which are educated, very deductive, very looking for small optimizations, while the world of art, there is the creative to have new ideas. To bring this together, idea one thing is this design thinking. But today I have the honor to start with this technical session and to try to take you behind the scenes of what is a hype today, which is artificial intelligence. A short statistic about the Hasso-Plattner Institute. There are a relatively small number of students, 600. The idea is to give them a very personalized training. Compared to them, there is a large number of PhD students, 170, many here in Potsdam, but also in our out branch in Israel, Technion, in South Africa, Cape Town University, Nanjing in China, in University of California in Irvine. There are in the moment 15 research departments, and we are just increasing. So we have a new area, a new couple of departments in the area of digital health. And we are going to establish something similar with digital energy. So the institute, financed by Hasso-Plattner, gives the idea to educate future leaders in IT technology. And this will change our life in all perspectives, this digitalization. Something is really behind the scene, many advanced. Some things are not just started. For example, digital education in the schools in Germany, so it's the systems, the society has difficult to adapt innovation to go with this. But it's no secret. Digitalization, we have no chance to look back how former generation dealt with that problems. Every time with a new technical development, one can look backward and see how they did before to have this. This is a completely new world with different rules than the rules of our physical world. We are trained by evolution to deal with. With this digitalization, speed does not play any role. Space concept is useless. Time is the speed of light. So there are many things changing, and particularly the new activities which called in the research world artificial intelligence. Here are some what was done in HPI. So we have to develop a German infrastructure for schools. We have in security, in recording, this MOOCs, this massive open online courses. There is a platform, Open HPI, if you are interested to learn something about digital things, security or other things. It is a good place. But today we want to speak about what is machine learning. See, it is a hype with AI in Europe, Germany, also in the US. And it's not the first hype. First hype, AI hype, was in the 50s last century, when the computers start to come into real life. Then the people, the novel writers start to think what could happen if these machines take over the power. Then we had in the 80s, 90s last century, also an AI hype. And the idea in that years was when we do any kind of decision as humans, we follow rules. So the idea was, if we program all these rules in a computer, then computers are able to make similar decisions like we. It didn't work. You know, it didn't work. We do not follow so much rules. Every time in similar situation, we behave in a different way. But this time, the third hype now, it's based on this machine learning. And this time, there are some real success stories to report. The basic why this time it works is we have a huge amount of data. Data which are digitalized. So we can really start to think, let machines learn from that data. We have hardware which is much more powerful than the years ago. There are parallel computers, there are graphical machine cards so that brain structures can be simulated. Cloud computing is a way that even if I have only a low power computer, I can connect via the internet and can get any kind of power, computational power I need. And then the deep learning algorithms. Here are some, sorry it was, some data about what is going on with our society. Amazon offers 550 million products. 550 million products. 2.3 billion people use smartphones. And the smartphones collect data about their movement, collect data about what they are interested in. There are, this is also very impressive, 400 hours video that are uploaded in 1 minute to YouTube. So when I speak about big data and material that machine can learn, then it's such kind of data which make it possible that machine learn. And more such things. This new deep learning algorithms are very successful in recognizing the content of images. They are in the same, meanwhile, they are at the same level like we humans. But understanding images is difficult. It's also difficult for us humans. Here are only a few examples. And we have to look careful to see what it is. And sometimes we do not correctly say what it is. And now we ask machines to learn from such data to self-standing see what's going on in the image. So this current technology, which is so successful, is this deep learning. There are no more any kind of algorithms programmed to the computer. There is a computer network, convolutional network that's organized a little bit like our brain, and then this system one shows images to that system. And after 1 million images with an explanation, this is a cat, this is a dog is running to this is an house. After 1 million is only a big number. After 1 million of such images, you can show the computer an image without explanation, and it's highly probable that the computer says correctly what is on the image. From this 1 million, computer learn similar like we are trained. This representation learning, this was 30 years ago with this rules-based. Machine learning starts very early so that machines are able to adapt some environmental data, for example, your heating system, learn when weather is changing and adapt to that. So there is a broad range, but what is, when we speak today about AI, then it's this deep learning. And this deep learning follows the same way like our brain is organized. You see here that when we start to see this on the right side on the button, then in our brain what we see are single light points with special color. And in our brain, these points and these structures are put together. First, we learn where are curves. Then we realize areas. Then we realize eyes or mouths. And at the end, all together gives us the impression of an image. It's done very fast, so computers are not so fast, also they are very fast. But one tries exactly to organize this computer networks, this convolution networks in such a way that they get an image, so the computer immediately understands all the pixels. But from the single pixel, you cannot conclude what is the sense of an image, what is the content. After a while, you can see edges, you can see forms, and then you can see, for example, eyes, and come closer and closer to them. The problem, one needs this million or this many images to train a computer. And here are this image net data. This is a huge amount of images which are presented to a computer in this training phase. And then, this is fixed data set. And so in the research, the different research group try to improve and improve and to improve. So there's a competition who has the best architecture to learn from this data and then to make the test and prove that the computer is able to realize the things without help. This ImageNet challenge, here on the right side, you see over the years that the accuracy, this is what is measured. That is, over the last 10 years, there is a huge development. And this development was reached because these networks become larger and larger, so it's more and more power. By the way, all these research results from today, AI, if this would come into practical life, the world would need 20% more energy. So in the moment, this is research. And we have to strengthen our research to come up at the end with really practicable things. But in the moment, there is a fight who is the best in recognizing what is the sense, what is the meaning of an image. One says that there is about the accuracy of humans, also not 100%. So it is typically saying that it's about 6-7%. And here you see the success in the compared of the artificial networks compared to the human abilities. Also, this is a timeline to the present, and this deep learning is most successful in image recognition and in speech questions, understanding speech for translation, for making subtitles and other things. And in both areas, the most advanced machines are better than humans. Sometimes one speaks from island talents. So some more trivial things computers cannot. But here in this area, they are very, very powerful. And so what is done here is a human brain, and a little bit the way that it starts from recognizing edges to some single structures, eyes, nose, mouth, up and end up with putting this together in a face. And you see going through the train that there are different regions which contribute to this recognition process. And here it's about 40 to 60 milliseconds. The edges are identified. This area, the eyes, nose, mouth, the substructures are recognized. And here, altogether, the face is recognized. This is a very rough idea how these networks are designed. There are, on the left side, the input layer. There's the single points of the image or the words or the text are put into this network. And then there is a number of hidden layers. It starts with 100,000, 10,000. Meanwhile, these are very, very complex structures. And at the end, there is an output layer. For example, which tells the meaning of an image, or that gives a text, or that gives a translation of a text. This depends from the purpose the system is trained and worked for. And inside these hidden layers, the single points do some relatively simple mathematical operation and report the result to the neighbor processors. And they report to their neighbors. So in this way, over the time, the weights, how this information are distributed to the neighbor, are changed, are calibrated. And at the end, after the training phase, it works well. So it is in hierarchical feature learning higher abstraction. And this is, from the nature, difficult for computers. Yeah, you start here with giving in some pixels and end up over these structures by something like faces. So here another illustration. So in the first layer, if the inputs are given in all these points, in all these different points, one can almost see nothing. There are colors, there are a little bit. In the next round, second layer, you see in the different points more structure. And the more the system works with these hidden layers, the more structure you can realize and is detected. These are the architectures and the number of layers over the time. So it starts with very simple to try to create such a network, and then the people start to investigate and use more and more complex architectures, and the complexity is the different layers. Sometimes also there are feedback going to earlier layers. You see over the side these earlier layers that things are shortcutted or sent back. There, the competition is who comes up with the best architecture. This is to show you a little bit illustrates this learning effect. I have here something from a completely different area, but it tells how it works. This is the network on the top, and these are cars that need to find out the way out of a complicated street structure. And what you should observe is over the different tries for the cars, how the network is changed. Changing is illustrated with colors and with its bigger color, it's a bigger line or a smaller line. These are the colors. These are the colors. The data that are processed in one point are multiplied as an input for the next one. And the right calibration, the right finding, the right factors for each of the 100,000 of connections. This at the end is what makes the system useful. So I start. I start here. The cars are sent out, and you see there's a change in the network because it was not the correct way. Next round. It goes faster and faster, and every time the network is changed, is calibrated. This is what the factor that is the output of one such neuron is multiplied as an input for another one. And you see the car longer and longer, and it's trained to see curves, it's trained to see straight lines. And from all these things that do not happen, I do not know whether, no, it's not the end. It is trained, and later on you can use this trained network to use it in a car for self-driving and finding its way, even if the streets are not in a Caro pattern, are complicated one. It's a little bit a fake because it's very fast that the system is learning. Typically, you need much more rounds for this. This is the reason that so much energy is needed to train such systems. But I think, boom. But I think next. And every time you see the network is changed. This is the brain which controls this. So not a program that's given by programmers, it's self-learned by the architecture. So what we give in is the architecture and the structure of these networks and the convolution operations that are used. Not learned enough. As far as I remember, 15 is. So the change has become smaller because it's better and better trained. So it's more and more adapt to the last things that need to be learned. Yeah. So this is only for illustrating a little bit. Typically, one wants to recognize images. One wants to understand language. Huh? You see now, not only one. Many make it. System is trained. Of course, this huge architecture is not needed by the researchers to put together by their own. There are frameworks so that one can play with the structure. If one has powerful computers, here are some of these frameworks. There are a lot of use cases. For example, chatbots. There is a while, at least in Germany, if you call to a service of a company, of a system or product, people were very unfriendly. If you observe this in last time, people are very friendly. But no more humans. It's typically chatbots. Which answer you at least the question, 80% of all the question. If then there comes some special thing, then of course one has to go in more detail and then it's transferred to a human to take it over. Autonomous driving is something like the people dreamed to go to the moon. People speak. The metaphor is liked by the people, but I think it needs a while before we have this, and I like to drive my car. I'm also not waiting for this. Advanced security analytics. This is an interesting case. This is difficult. Here it's difficult to give the computer training material. Training material should look like this is a secure network, and this is an unsecure network. But we cannot say this is a secure network because then there is find some thing which shows after a while that's not secure. So here it's difficult to provide learning materials. So a little bit what we are doing as HPI, and after my talk you heard some of the examples what can be done also in the area of archives and art. So we try to recognize scene in an image. We like to recognize scene text. So meanwhile, there are good programs to recognize text, recorded texts, to change this picture, this PDF, into a word. But if the text is in the scene, in TV, car is going a street and there is a name of the shop, you see it from this and different angles. This is difficult. But this type of text gives some information about what's the movie going on in that moment. One looks for metadata to explain this video is about that situation. You know, for text, we have Google. Works perfect. But for videos, we have nothing. We have something that looks for the name of the videos. But to look a special scene in a special situation in a movie archive. We are at the very beginning. And if you see 400 hours video in 1 minute by YouTube, this only by machine help can be used. Then a medical image. Medical image is very promising because it is even for humans very difficult to understand these medical images. Black, white, coming from the different images. So it needs a long training to do this. So if there is enough material, annotated X-ray images and others, then the machine can learn this and can become more precise in the judgment than humans. We have also faced to this energy problem. So we try to change these architectures into binary networks, because this would reduce very much the energy need if there is no computation of two numbers necessary, if it's only single logic operations. And then, of course, for our teaching material, automatically understanding the spoken words and producing subtitles. Here is the media analysis, so to recognize events, what's happened, for example, in a camera, the surveillance camera, to see whether someone goes to his car, open it and drives away, or whether it's a criminal who tries to take the car. Automatically, by analysis of images, and it's possible. So here you see that it's possible. I go a little bit fast. I will not go. There's another movie which shows how these machines detect text in scenes and then understand these scenes. Perhaps I show this here. Ich habe doch Text. Danke. Ist alles? It's done by a machine. For humans, it looks trivial. This is something, this is interesting. This is something we have problems. The second layer behind, this is ironic. This, of course, machine today are not able. Okay, medical processing, I already mentioned this. Also here, the huge amount of medical data needs machines to analyze this data. They more and more produce with a scan thousands of images, and to analyze this for humans becomes more and more difficult. So automatically, brain tumor segmentation, this was a PhD thesis with run now is the doctorand Nina Resai is in Harvard. This is cardiac segmentic to recognize automatically and to see what's ill, what's not ill. These are the binary networks we try to produce to face the energy problem. So this is sometimes interesting for me. We have a big discussion about climate, but such topics which are really of interest, they are not discussed. Why we need energy and for what purposes? No one says AI is bad. You can say AI is bad because of the huge energy. But as a researcher, you are forced to think how we can reduce this and hold the same accuracy like in the other. So this is, I go a little bit faster. Here, this was the introductory, and we are not, of course, as well here in Barberini, as well in the institute, the Hasselblattner Institute, thankful to the foundation that it helps us to do such interesting things. And of course, we can also use artificial intelligence in art. Of course, you will smile, but we simple engineers, we think we contribute something. So this is our main building of the institute. And we like to have it as a painting from Van Gogh. So we can learn from all the Van Goghs, put it together with our main building, and now we have a really valuable image of our institute. The idea is simple. There is the input of the different, this is only one example, of the style of one painter, which is learned in detail. Like the images you saw with the cars, like it's learned in a detail. Then I give in a photo, and then in the middle, this gray things at the end of the network has unified both system, has taken the photo and has used the style elements which are characteristic for this image to do it. So if there is no more money for buying valuable images, we can help to produce. Thank you for your attention.
Professor Meinl, is this on? Yes. I'm just going to reiterate, we're going to save questions for the end. I'm sure we all will have a lot of them by the end of this session. I'd like to introduce to you now my colleague, Martin Lawrence. Martin is Director of Technology at the Wildenstein-Plattner Institute. He studied IT Systems Engineering at the Hasso-Plattner Institute, where he finished with a master's degree in 2010. After that, Martin was working as a PhD candidate at the research group Enterprise Platform and Integration Concepts, or EPIC, at HPI. In 2017, Martin joined the Wildenstein-Plattner Institute as Director of Technology, where he is responsible for building a research and digitization platform for art historians. So it's my honor to introduce my colleague, Dr. Martin Lawrence.
Thank you, Elizabeth. Welcome, everyone. As introduced, my name is Martin Lawrence, and I'm the Director of Technology for... All right. Is that working better? Yeah. All right, thanks. So you've heard the last very tech-heavy presentation of the day. I will take one step back and try to explain to you where we see application areas of this basic research. And as an institute that is probably very similar to the institutes that you heard today, we are thinking about ways how to incorporate this into our digital platform and information systems that we provide and that we develop at the institute. So one step back before we dive into the very details of what you heard before. Where is the... here's the presenter. The mission of the Wildenstein-Plattner Institute is to compile digital catalog resumes and archives that support research in the field of art history. Before we dive into the details of our archive, let me take one step back and explain briefly what we use our archives for and what type of challenges we're facing. Oh, sorry. Looking at the wrong screen. We generally follow an evidence-based approach where facts in our publications are backed by documents from our archives. Our founders envision an institute that has access to state-of-the-art technology which should support many aspects of our internal operations as well as deliver value for the art history community at large. Consequently, a large part of our activities in the last couple of years was dedicated to the development of a digital research and publication platform. And that platform, I would like to introduce very briefly, consists of two main components. The first component is a catalog management system, which is responsible for handling artwork-centric information like provenance, publications, and exhibitions. And it also allows to do publications of catalog resumes. The second component is an ISA-G EAD compliant storage and description system that basically represents a huge repository of digital archival material. The data structures that I outline here very roughly include information about agents, exhibitions, artworks, auctions, and publications. The main concept that links and that basically glues all our information together are events, art events. And we have the system is designed to connect all the things that we collect information about with archival material, which in our case we call resources, which are again attached to media elements that you can imagine as pages of a sales catalog, for example. From an artwork-centric perspective, the catalog component allows to link specific artwork information to resources of our archive. Here, I just selected a random sample from our cataloging system. It's the artwork La Prairie Fleurie by Claude Monet. And I'm showing you this first provenance entry, which is directly connected to, for example, sales catalog in our archive. And if you click on that record, you would be able to jump into the archive and that page would open up where you can read basically and understand why we chose to publish that information. The second example is for an exhibition record where we link to the exhibition catalog, where you also have the list of artworks that were shown in this exhibition. The big challenge that we face at the moment is the digital transformation and accessibility of a massive physical archive. And I would like to focus on that concept of accessibility. And I'm certain that a large part of you has quite a bit of experience with online archives. Some are better, some are worse. And I believe that quite a large part of that experience with these archives can be discussed focusing on the difference between accessibility and availability. Availability, although the semantics of these words do not seem to be very different, I believe that there is a significant difference when we look what this means for an online archive. Availability can be achieved rather simple by means of scanning and storing documents. I'm sure that people in the audience who own a reasonable sized collection would hardly agree with me when I use the word simple to describe this process. But let's focus on the technical feasibility here. A basic digitization pipeline would look something like this. With just a little bit more, you can improve the quality of your pipeline quite a bit by adding, for example, an OCR step. And I think that's common vocabulary for everyone that has dealt with digitization for archives. The aspect that I would like to focus on is, in order to create an accessible archive, you would need to consider the performance, the scalability, and the data of your archive. And I think the performance and the scalability aspect are pretty obvious to everyone that has dealt with information systems. But let's focus on the data part. So why do I think, or why do we think that data is a key aspect of a good archive? If you have data, and especially a lot of metadata, you can create intuitive user interfaces. You have powerful search capabilities. You will be able to guide your users through the system. And of course, you will have accurate and relevant search results. To create metadata for your archive, you have different means. Usually, there are two steps in processing archival material. The first is image analysis, and the second one is information extraction. You could go ahead and use manual labor to do this, and I think most of us have done that in one or the other way. So you could start by transcribing and translating your material and put that in the database. Next step would be that you start indexing, tagging, and creating manual references and linking. While that is a valid option, manual labor is usually expensive and it doesn't scale very well. On the other hand, there are new developments in AI and machine learning, as we heard today, that are getting more and more attention and that are getting a lot more advanced. I'm not going into the details of every recognition technique that you see here. There will be more presentations that will talk about that in more detail. I would like to give you a small example that may help you understand where and why these techniques would help an archive to become more accessible. What you see on the right side is an archival material that is easily found in any archive. It's a mix of textual content and handwritten text. And if you do the first digitization step, you just scan the material and you already collect some metadata, which is probably not really relevant for an art researcher, but it might be relevant for some type of queries. So for the sake of simplicity, I just recorded format and the file size here. The second thing that you could do is add in text recognition step, OCR. We discussed this already. I would consider OCR at the moment commodity technology. I just pasted a small link, which I use. You can go to the website. It's the Tesseract.js, which is a system which is a website where you could just drag and drop this type of document. And I'm not sure if everyone can see it, but you see these small red bounding boxes in the document, which basically means that the system has recognized some characters on the document. It even recognized the handwriting. But, and I'm again not sure how good you can see the left side of that slide. Some of the information got recognized pretty good. The handwritten text is pretty much gibberish and you cannot deal with that. So the next step that we could do is add a handwriting recognition step to that pipeline that we use to process our material. And at that point in time, you would already have information that is very relevant because it contains information about names and it contains information about places. And that information is basically lost if you haven't had someone that described the document. And at the scale that we talk about, it's hardly possible to find people that process the entire material. So the next step that you could do, and that's basically the more advanced techniques that will be introduced later on, we're looking into something called entity recognition, which is basically taking the text that you have that was transcribed by a recognition system, and it adds semantics. In that case, right, I should not use this laptop to check. You see that, for example, we can recognize people, we can recognize places, and we can recognize dates, for example, which from normal text, you know, it's just text, and if you have a full text search, that will most likely present you with the correct page, assuming that you enter the right text. But in some cases, you want to say, I want to see documents that have dates in the range from X to Y. At that point in time, you know, it's not possible to do this with a text search anymore, but your system should have understood that there was a date in the text and it was a date, and at that point in time, you could actually connect that to information that you have in a database. So, apart from the two techniques that I introduced in this example, there are a lot more other, techniques that are out there and that can be used to increase the value of the archive in different steps of the digitization pipeline. The current state of our archives looks like this. We have about 85,000 the number of archival resources that we possess at the moment is about 85,000. We have about 12 million digitized images, and that consumes around about 10 terabyte of storage. An ideal digitization pipeline could look like this, where we would enhance the basic pipeline with the capabilities that we use right now to incorporate the options that machine learning and AI are providing to us. Now, before I close my presentation, I would like to give you a small outlook of what we expect to publish in the next 3 years. And I hope that, at least in part, some of the concepts and technologies that I discussed today will have an effect on the way that we present this material. Thank you very much.
Thank you, Martin. The next speaker we have this afternoon is Christian Barth. Christian Barth is currently a PhD student and the chair of Internet Technologies and Systems at the Hasso-Plattner Institute, University of Potsdam, Germany. Prior to his PhD studies, he received his master's degree in IT systems engineering from HPI in 2016. His current research interests revolve around deep learning, especially computer vision for text localization and recognition with weakly supervised methods. Christian Barth, please.
Hello, everyone. So today, let's get a little bit more technical and let's dive into handwriting recognition and OCR as such. And maybe I can help you and just show a little bit how we could maybe help you as art historians, if you do research, with this automatic way of analyzing your data. All right, so let's have a look at the short agenda, what we are going to talk about. So first, the whole question, like this automatic analysis, how might it help and why actually might it help? Then what are actually the challenges we face as computer vision researchers if we think about automatic document analysis? Then I will try to give you a short glimpse into what we actually do and just try to explain an approach we are actually trying to do right now to you. And then let's have a look at what we want to do in the future too. And all of this is in place in a project we do together with the Wildenstein-Plattner Institute. So we also basically are working on this kind of data and this on their archival data. And so if we dive into the topic, we just let's have a look at this pipeline we've just seen by Martin. And so the question is like, where are we in this case? So we can place ourselves like in the middle. As he already said, that we are trying to do like image analysis. We have images of the documents, and we try to analyze them to try to find text, and maybe also try to analyze and find images that might be in those documents, which are images, those images that might be in there. You will see some examples in a second. So the question is, what are applications? I mean, we've heard about possible applications today quite often, but let me just put them again to you. We want to enable metadata search, right? So we just don't want to know, okay, this is an image, but we want to know what's in the image. So what kind of information do we have there? How can we find it? And basically the idea is also, and that's actually the big hope, that we can actually support and just say, okay, you're right now looking at this kind of document. Maybe this is also interesting for you because this also contains information that could help you. And that's, I guess, it could be quite helpful. That's basically the basic idea. And so the first question is, why is this not done already? Why is this a hard task? All right, let's have a look at it. I got a nice example for you. So look at this picture, please. What do we see? We see a man with a camera, and he's standing on some kind of field, and there are some buildings in the background. For us, this is quite easy to understand. But if we let a computer look at this, he's basically just seeing numbers, nothing but numbers. This case, for us, it's also quite easy to understand that there's some kind of structure in this image, because we now have it in a two-dimensional grid, and we can see like all those numbers, they are shaded in different colors, depending on their value. But if we don't have that, we would not be able to see that much anymore. And so this is the same a computer can actually see if he's looking at this image. So you can imagine this is quite a difficult task for a computer to actually get any information out of this image. And so this is the first thing, which is basically the biggest challenge we face. But what's a nice thing about the whole thing is scalability. So I got an example for you here. If we talk about scalability, it's the Jeremy Bentham collection. Maybe some of you might know it. So this Jeremy Bentham, he was a famous British philosopher from the 18th and 19th century, and he did a lot of writing and wrote lots of his ideas down. And there are roughly 60,000 pages, or folios in this case, that have to be transcribed. And in the late 50s, they started to make efforts to actually transcribe those folios by art historical researchers. And so in 50 years, they've been able to transcribe around 20,000 of those folios, which is quite a lot already, but that's 50 years, so which is quite a long time frame. But since 2010, they've been able to actually transcribe 20,000 more of them, which is just like 9 years. So the question is, what changed? In this case, well, they tried to use crowdsourcing, as we already heard today too, which is a quite effective tool. But if we think further, so if we could use our computers to do this kind of crowdsourcing work, just to do the first step, we can actually be pretty fast. We can analyze one image or just one document in some seconds, and we can actually also parallelize this. If we think about cloud computing, where we have millions of computers, we can just do all of this like in a very short time, if we have the technology available for this, of course. But the problem is, the results, they won't be perfect. I can assure you this, because the way we work and the way those algorithms work, they will never be perfect, like 100%. What you would normally expect from a computer to be like perfect, because they calculate and they are always right. In this case, they are not really. It's just the way those algorithms work, because they are, as Professor Meiner already said, a little bit similar to our brain. And so we are not always perfect, so the computers in this case also not always perfect. But we can still try to use this and maybe later on have some humans proofread or check this out. Might be possible. So this about the whole idea of why it might be interesting. And so let's have a look at what we can actually do today. So what's out there, what's actually already working for automatic image or document analysis. Martin already said that there's optical character recognition for printed text. And so I got one example here where we have lots of printed text on a page. We could read this with a computer very easily. This is not really a problem. And if we go on and further and think about what we could do too, there's not much more we could add to the list. Basically, not really anything. So all the other things we could do, they're basically in research. And so they're not working. They're not really like commercial products that we could use for archival data. And so what's basically missing, what's interesting is the optical character recognition for handwritten text. As you can see, some examples here of some catalog or also some notes that researchers have taken. And those this kind of data is quite interesting, I guess, also especially for you because, well, I don't know, it shows some information about like what kind of prices did we have, what did the researcher think while he was looking at this, or like also the owner of the archive for just writing it down, maybe also for helping you to get a better idea of the time frame from when such a document is from. And for us, this is quite interesting research to me because, having lots of archival data, which is basically that's history, just helping you guys. I think that's interesting. So that's why it's cool for us to also work with this kind of data. But there are challenges. And the challenges we have are definitely that if we have our computer and let's look at the data, the best thing would be to have something where we just have handwriting, which is the image on the right. I mean, it's already difficult to read, and it's in some kind of language, which I don't know right now. Could be French, I don't know, to be honest. And so, but it's also, that's the one thing, we have some kind of content, so we can have printed content, we can have images, and with the handwriting, like everything mixed together. And so actually the computer needs to understand what we have in there. And we have various languages it could be written in, and we have different eras it's from, so it could be quite modern handwriting, but it could be also quite ancient handwriting, let's say ancient if we talk about like 17th century or something, or even earlier, which is totally different from modern handwriting. So also the computer still needs to learn with this, and we have different handwriting styles and different people who are writing, and sometimes you just are not able to read anything at all. I mean, how should the computer be able to read it? So this is quite challenging, really it is. And what comes to mind if we talk about archival data, especially from the Wildenstein-Plattner Institute, the data, we do not have any annotations. That means we don't know anything about those images. But I will come to this later a little bit. So, I mean, I said there are no commercial things available for handwriting recognition. Actually, there kind of is. I mean, there's a system by Google where you could basically try to do handwriting analysis on a document. But this API is basically just meant for quite modern forms where you can just like use this to recognize the handwriting which is in there and stuff. And for instance, this is also a research effort for Microsoft where they try to classify if on this image you have or on this document where there are signatures and where it's just handwriting, there's just some kind of handwriting. And so the green box you can see there, those are signatures. So the computer classified this part of the document as signatures, and all the blue boxes, they are just some handwriting, basically. And as I already told you, what's missing, so the computer needs to understand the structure of the kind of document we have right now. So basically, some kind of content analysis is important too. So just that we know, is it just an image? Is it some printed text together with an image and together with some handwriting? Or is it just handwriting? So because in order to do real good analysis, we might want to know what's actually on that image. But also this content analysis comes with quite some challenges in this case, because we have also a variety of content forms. We could have some covers of a book, like the left image here, or we could have letters, we have postcards. I mean, you know very well what you have in your archives, which is like quite diverse, and I've already seen today quite diverse, let's say, documents and examples. And again here, we still have the problem, it's not really annotated. So we don't know what this image really contains, not always. So the question is, what can we actually do if we don't know anything? So what we try to do is, we try to use machine learning, who would have thought, to just extract the semantic information we have in our data, in these images. And the problem is that we cannot use state-of-the-art methods, which are there. There's research going on in this direction. But if we don't know anything about the data, we can't use the state-of-the-art methods, so we have to come up with something else. And the way we are trying to do is that we try to come up with methods where we actually generate data by ourselves that's somehow similar to the real data we have, and try to use this in order to classify or just make sure and do our work. And I got some examples of artificial data here for you, like on the bottom. On the left two images, they show some generated handwriting in an image, in a part of an image, and the right two, they show something else, which is not handwriting. Just keep those 4 images in mind. We will lead them later. But first, let me just reiterate again machine learning and why I'm always talking about those annotations, why they are important, and what's the problem if we don't have those annotations. So if we talk about machine learning, we have 2 phases. The first phase is the training phase, where we need to learn our model and just so that it knows what to do. And if we look at this image, we are with some nice flowers, and then we also know, which is the label, the annotation, that this image contains some flowers. And we have a machine learning a model which is just initialized randomly, and in this case it can do classification, so it's supposed to tell us what's in the image. And we have 3 different classes, which are dishes, flowers, or trees. And if we ask the machine learning model at the beginning, like, what do you think is in this image? It might tell us dishes, which is not right because they're flowers. So we would tell it, no, dear machine learning model, flowers are in this image. And then we use an algorithm, the backpropagation algorithm, that the model can learn, and it learns. So as you see, like the weights, the connections, they change. And if we ask it now again, it might say as flowers, and we're like, yes, that's pretty good. Now we got you. So you're trained now, you're ready to go into the wild. And then into the wild means we go into testing phase, and we take another image, which has no annotation, no label at all. And we ask the trained model, what's in there? And the trained model tells us, we do have flowers in there. We're happy because we have a trained model which can actually be used on different data than we actually trained it on. So, but as you've seen in the training, there's some extra we need to this label in order to train this model. So what we actually want to have, if we look at text localization in this case, so we want to localize handwritten parts. On the left image, you see what we would actually need for doing this training with state-of-the-art approaches. We would need the image or the document, and those green boxes, which will actually tell us the locations of the text so that the computer can learn from those informations, okay, this is something I should look for. But what we have is, in this case, with the archival data we got, only this image. So we don't know anything about it. So the question is, what can we do? Think about those images I showed you, and now you can see if we just take an approach where we just slide a window over this and just take always some little part of the image and just have a look at those little parts, we actually get a grid. And so if we look at each of these parts individually, we can actually try to use a machine learning model that gets one of those parts, and we just classify for each of those parts, does it actually contain handwriting or does it not? And if we do that, in the end, we can actually get for this image, this is quite coarse grain, but we can actually do it more fine grain if we do like smaller parts. So we actually just crop from each image. We can say, okay, each of those parts, the green parts, they do not contain handwriting, and the orange parts, they do contain handwriting. And so the basic idea here is that we use those artificial images I showed you before as training data for this model that can actually say yes, handwriting or no handwriting, and then use the real data just to actually do the analysis. We first train our model on this artificial data, and then we use this to find out where it's actually handwriting or not. And so this is what we are currently working on, just to finish this model and have something nice that can actually do that. And if we look into the future, what might be interesting too is so could we use, can we do more? Like can we find out what kind of text is there actually? So the next step would be to say we want to find out if we found the handwritten text, what kind is it? Is it a date? Is it some kind of price? Is it a name? Is it a signature? Something like that? Or is it just a drawing, as you can see here? And yeah, those are all some snippets that we found in some data from the Wildenstein-Plattner Institute and from the archive. And you can see it's actually also quite diverse what you can find there. So first, just giving a hint what's in there. And of course, the next step, which is the holy grail, we would say, is to have the text localization and, of course, complete text recognition. This case, I did not write down everything of those handwritten text lines because it would just be too much for the slides. But I guess you get the idea. That will be the next step to do. If we look at the time frame for this project we have here, so we started in March. We are right now in September. By the end of the year, we actually want to have this text detection localization prototype ready that can be used with the archive. Then we want to go on to make sure that we actually try to tell you what kind of text type we have. By the end of next year, hopefully a text recognition model, and then we want to put all of this together into an end-to-end system. We can actually do detection and recognition in one step afterwards. And then actually that's also currently the end of the project we're talking about. So for this, and of course, looking further into the future, it might be nice and interesting maybe to do, I don't know, you can tell me if that's really interesting or not, to have this scan of this page, and we have those images in there. And so it would be nice to do some kind of image recognition, or just object detection. What's in there? What is depicted in those images? And maybe you can also use this for further search and further research. And of course, as Martin already told us, further processing afterwards. Once we have those information, we can go some steps further and use the textual information and maybe also the information we got from images just to link all this data together. But we will have more input on this in the next talk. And so to conclude, I think automatic document analysis might help with by reducing the manual effort that's needed to get information out of the archive. And it should allow to intelligently use the data that you have in the archive by helping you to create a better understanding and maybe also support in more exploratory research, which might be helpful, I hope. So thank you very much.
Thank you very much, Christian. I'm just thinking about the hundreds of thousands of auction catalog pages that we scanned and the fact that we won't have to thumb through each page looking to see if they're annotated. That's quite a relief. So our last speaker of the afternoon, now evening, is Professor Dr. Rolf Krestel. Dr. Krestel is a visiting professor and chair of intelligence systems at University of Passau, Germany. Since 2015, he has served as the head of Web Science Research Group and senior researcher at the Hasso-Plattner Institute, University of Potsdam. Prior to that position, he studied philosophy and computer science at the University of Karlsruhe and obtained his PhD from the Leibniz Universität Hannover. From 2012 to 2014, he was a postdoctoral research fellow at the University of California, Irvine, and in 2014 was a postdoctoral fellow in the research school of the Hasso-Plattner Institute. His research areas include text mining, natural language processing, information retrieval, machine learning, and recommender systems. Thank you very much for coming, Dr. Krestel.
Thank you, Elizabeth. Yeah, I have the honor to give the last talk of today. I also try to keep it on the same level as the talks before, so no math formulas. Although you have to keep in mind that there is a lot of math behind all those things. Nevertheless, I think I can make it clear what we are doing without using any formulas. So, what do we have? We have lots of data, lots of different types of data, art catalogs, journals, auction catalogs, and all those different documents, they contain different languages. So this is a rough pie chart that shows the languages that we deal currently with, a subset of the Wittgenstein-Blattner Institute collection with. So most of it is English, but there are also French, Italian, German texts. And this makes it more difficult if we want to actually analyze text. And that's what I'm going to talk about with you. What can we do from a text mining point of view using these new text mining methods that were brought into the research community with this new deep learning frameworks that we heard before earlier. And especially for text, there is a special kind of deep learning method that really advanced the area of text mining, which are called word embeddings. So this is a way to represent text data and somehow capture the meaning of language. So this is something that computers were not able to do before. Before we had this deep learning revolution, computers treated words like numbers. Now we can actually treat them like having a semantic meaning. Apart from this very recent development, there are other mature technologies in text analysis that are also very useful to apply them in the art domain, methods to visualize text, methods to extract topics from texts, named entity recognition, relationship extraction, information extraction in general. So what we are planning to do is take these methods, put them all together in one system, and then adopt these components to the art domain. And this is particularly interesting because the art domain has certain challenges that you don't find in other domains. To make this a little bit more clear, I want to dive into details of the pipeline that Martin presented earlier. So now we are focusing on the text part, not on the image part. And this is actually a simplification. So I have it a little bit more complicated to give you an idea what actually needs to happen at the various stages. And this starts from the representation of the documents. Here on the left, we actually need to find a way to represent the words not just as numbers but as vectors. And this is the embedding step. So we want to take the words and embed them in a vector space. I will explain the different steps in more detail later on. So let's say we have now an embedding, we have a representation of our raw documents. The next thing that we want to do is we want to extract entities. So we have our text, we find some entities, and we want to identify them. In this case, it's the title of a painting, an artist name, and a year. This is only the first step. The next step is to link these mentions to actual unique identifiers to make sure that we are talking about the same Picasso and about the same image and about the same year. If we have this step, the next thing is to extract relations between these entities. In this case, we want to automatically extract that this painting was painted by Picasso in a particular year, and we can extract further information related to the entities, for example, birthplace. In another step, we can look at the topics that are associated to this painting, for example. We can look at what are words that occur together with this painting, and we can identify certain words that occur in this context. And putting all this together is nice to have, but what's also very important is to visualize this information. For this, we need to come up with a way to really visualize this whole information and not just let the user look at lists of long lists of entities or long lists of topics, but somehow summarize this. To give you now an idea how this works in more detail, let's go through the individual steps. So to start with the embedding, the idea that is the basis of the embeddings is quite old. It's from the 50s, and it goes back to a researcher called Firth, and he said that the meaning of the word is actually determined by the context. This is not very new in the language of philosophy, in the philosophy of language. We have this already earlier. So the context is very important to capture the meaning of words. And this idea was very successful recently in natural language processing or in automatic analysis of texts, because it helps now to give meaning to words by looking at the context. So you represent a word by the context where it appears in. In this case, we have the word house. We can look at the words that appear around the house, and we can then use the context to actually represent the word house. If we do this, we get vectors, and the nice thing is we get now similar vectors for words that express similar meaning. In this case, house and mouse, for example, they only have one different letter but a completely different meaning. But house and home, they share some semantic meaning. That's why the vectors are more similar than the vector to the word mouse. And these kinds of representations can be learned with the deep learning technology that we have seen earlier. So we have these networks, and we can learn how this network needs to train its parameters so that they actually end up with having similar vectors for similar words, for similar semantic words. This results then in what we call a word embedding. So every word is then represented as a vector. And traditionally, computers have represented words with just IDs. They just numbered the words, and then every word gets a number. And this is not really helpful if you want to find similar words, for example, because they are completely differently represented. For these word embeddings, there are different ways you can use them. So you can use word embeddings that were trained already on a big corpus. The big companies, they offer to download these word embeddings, Google or Facebook. They have lots of training data, so they can learn very complex word embeddings, and you can download them and then apply it to your collection. If you happen to have a big collection yourself, then you can train your own word embeddings. And for special domains, this is necessary because the language in different domains differ greatly. So in another project, I'm looking at patents, for example. And if you ever try to read a patent, you will realize it's not easy to understand because although they are in English, they use a special kind of language. And in the art world, it's a little bit similar. There are certain terms that are only used in the art domain, or they have a different meaning in the art world than in another domain. So you want to actually train your own word embeddings if you have enough data. Okay, so that's the idea, how this should work. And now let's have a look if it really works. So this is an example of a word embedding, and you can look at the word frog, and you can actually look at other words that are in this vector space close by to this word. So which vectors look similar to the vector for the word frog? And then we see, then these are the top 7 words that come up. Okay, the most related term to frog is frogs. This makes sense. This is probably related. Toad makes also sense. Then there are some other words that I didn't know, so I looked them up, and yes, they all make some sense. So they're all kind of closely related to the word frog. And this is very nice, and this helps us now to build on top of it our algorithms and our detection and classification methods. But this is not enough. So with these representations, we cannot just find similar objects. We can actually do mathematical calculations. So we can answer analogy tasks of the kinds that you get if you do an IQ test or you do a test to be accepted at university. You have questions like king to queen is like man to Did somebody pay attention? So this works here because we can now, in this vector space, do exactly these calculations. This is an example where we exactly have these gender terms, and we can see that the vectors all have a similar direction. And we can do this for all kinds of words. These are the vectors of companies and the CEOs of these companies. And again, you see they are also very closely aligned. That means you can ask questions, who is the CEO of a particular company? And you can answer this by using these kinds of models. So this is a two-dimensional representation to make it visible. In reality, these vector spaces have higher dimensions, maybe 100 dimensions or so. But this works very well. And you can also look at grammatical test cases, for example, to identify comparatives and superlatives. So here you see that strong, stronger, strongest has a similar trajectory than short, shorter, shortest, and dark, darker, darkest, and so on. So these word embeddings really capture semantic meaning that was not possible before. And the question is, how can we use this now in our art world? And you can think of many possibilities where you can use this. The most important one is as a pre-processing step, so as a presentation for further processes. But you can also use it directly to find interesting data points in your data. For example, you can look at these vectors again, but now you look not at the vector between a company and a CEO, but you look, for example, at the vector between an artist and a certain painting. And then you can ask, okay, how is Da Vinci's Mona Lisa related to Van Gogh? So what's Van Gogh's Mona Lisa? Given your data, and then you might end up with something like this. Maybe in this case, it could be the most popular painting or whatever it is, but you can learn these kinds of relationships, and you can find interesting new relationships. So this is the first part that you need to do. You need to represent your data somehow, your text data, and a computer needs to understand it, and these word embeddings fulfill this job very nicely. The next step is entity recognition. We also already heard from Martin the idea behind this. So we want to identify artists, we want to identify dates, but we also want to identify, for example, painting titles. And this is something that state-of-the-art tools cannot do nowadays. What state-of-the-art tools can do very well is read newspaper articles and annotate newspaper articles with named entities. And they do this so good that people trust their money to these systems. A couple of years ago, there was an incident where a newspaper republished an article from years before, and the article was about a company doing not well. And the result was that the shares of this company dropped in value significantly because there are so many automated systems that read news articles, extract entities, do a sentiment analysis, and then instantly sell the shares if this is a negative report. So this was a big scandal because the newspaper article was not up to date. It was just an old article, but the systems catched it, and this led to a big problem. But it shows these techniques are kind of matured for newspapers. They are not so matured for the art domain, and this has a couple of factors that are associated with that. So first of all, titles of paintings are very difficult to identify because everything can be a title of a painting. And there are other challenges associated with it. For example, you could have partial matches. So these paintings all have head of a peasant woman in the title, but it's not clear where the title starts and where the title ends if you read it in a text and you don't know that there are these different kinds of paintings. Another problem or challenge is that you don't know the type of the entity. So Jacqueline could be a person, could be also the name of a of a painting. The same with King George or Mona Lisa. The same with locations. So a painting could be titled Potsdam or Paris, but this could also be the city Potsdam or Paris. So you need to identify what type of painting it actually is. Since we were not really happy with the results that we get with state-of-the-art tools on the art domain, we developed our own named entity recognition in this context to improve a little bit. And as you can see, state-of-the-art tools here as baseline, even if we relax our measurement method, they only get like 8% recall and 20% precision. So this is not really high. That means they miss a lot of painting titles and they don't find the right ones. So what we did is we improved a little bit on that by incorporating special training data and using existing frameworks with this kind of new training data. And this already improves the result significantly. As you can see here, we get a precision of 40% and a recall of 30%. This is still not good enough, but it's a start, and it shows that there needs to be more research in this field. So next step after named entity recognition would be then the named entity linking. So we want to identify which entity is really meant with a certain mention. This is rather easy for somebody like Picasso because there are not so many Picassos relevant in the art world, but there are lots of other names where it's not so clear. And even for Picasso, he's referred to by lots of different names. So you have to find out that this is in all the cases actually one person that is meant with all these different variations. And this does not account for typos and OCR errors and so on. So this comes on top of it, which makes it complicated. So this is one way. We have many names that identify one object. We also have the opposite. We have one name that identifies many different objects. And it's not clear how you would find the right water lilies out of your whole repository of water lilies paintings. So what is typically done is you look at the context of a mention. So you have to decide which spring is meant. So first you have to identify that spring is a title of a painting and not the season, for example. But let's say you have done this, then you need to decide, okay, which of these two spring paintings is meant. And you can only decide this by looking at the context. This is also how humans would do this. And then again, you look at the named entities in the context, and then you can find out that in this case, it's the left painting that is referenced in this context. And if you have done this, if you have your named entities recognized and linked to a database or to your IDs, then you can look at relationship extraction. And you can actually build a whole network that computes and that shows the different relationships between the entities that you have in your collection, in your archive. And you can extract different relationships. Either you can formulate your own relationships. Maybe you're only interested in paintings and painted by and the artist, or you can let the machine learning algorithms extract all relationships that it can find. Depends on the use case that you have. This is very interesting work that needs to be done. Nobody has done this for the art domain. People are working on this in a general domain. Typically, they use Wikipedia and try to connect all entities that are mentioned in Wikipedia. Also, Google has a big project where they try to build a knowledge graph that connects all their information that they have. But for art, this is missing so far. A next technology is topic modeling. This is a little bit an older technology, well, old in the sense of computer science, not in the sense of art. So I'm talking about 10 years old. And what topic modeling does is it also looks at the context, and it comes up with words that are grouped together to form topics. So this is some of my previous work where I looked at computer science research articles, and I trained a topic model to identify the different topics that these article collections contain. And what you get is these topic lists, and every document gets then associated the different topics. And you can use this for a variety of tasks. You can use this to summarize your collections or part of your collections. You can visualize it, make predictions, personalize, and analyze your results. And how does these topic models work? So again, just a very bird's view idea. You can compare this with the astronomical models where you, for example, have the heliocentric model that says the sun is in the center of the universe and the Earth rotates around the sun. We know that this is not a correct model, but it's a useful model in a sense that it can be used to predict certain facts, for example, day and night. And the same with topic models. The idea here is that a text gets generated by an author who picks first topics and then picks words from these topics. We know that nobody writes texts or articles that way, but it's useful to explain why certain words appear in the vicinity of other words. And that's why these topic models are very useful, because they somehow model the way that humans could potentially write texts by picking topics and then words for each topic. And in the art domain, it could be very interesting to use these kinds of topic models to answer questions, for example, which other words occur together with certain entities. So what artists are always found in the context of certain topics, or which topics are formed by different entities that we are interested in. We could look at certain entities that are only mentioned in a certain context. We can also look at topic occurrences over time. So this is a study we did with NIH funding, and we looked at breast cancer funding versus lung cancer funding, and you can actually see how the funding changes over time by looking at the different topics. And something similar could be done with in the art domain as well. You can look at how popular are certain topics for different times. And you can also look at how topics change over time. So this is an example of the New York Times corpus. And one particular topic, in this case energy, and how the topic changed over time. So how do people, or in this case the New York Times, write about energy? What are the words associated with it? And something similar could be also thought for the art domain, if you want to see how different genres were, for example, seen in different time periods. Last but not least, it's very important, if you do all these nice, fancy computational things, you need a way to represent it to the user or to the expert or to the researcher. You need to visualize these things somehow. And this can help you to summarize what you have in your collection. It can give you aggregated results. It can give you the possibility to drill down, to look at different facets of your data. All these kind of information systems, what they also need is, of course, a link back to the original data. Because in the different steps, there can be errors introduced, and you want at the end possibility to easily verify that, yeah, indeed, this is what's also in the original raw data. So I need this to go back, but I need also some way to summarize this. There are existing visualization methods, for example, things like word clouds that can be used, but also more elaborate things that information systems nowadays offer. In another project, we looked at email corpora. And this is our user interface that we came up with. So you have the different topics. You can browse through them. It's kind of an exploratory system. You have a timeline where you can see who talked about what categories, and so on. So this is one way to look at the data. But it can be much more elaborate. So this is some research work that we are currently working on using these embeddings and visualizing these embeddings. We have seen earlier today graph data is very interesting, networks is very interesting, but we are actually working on how can you lay out the network in a meaningful way. So it's nice to draw a graph and a network, but state-of-the-art tools, they just draw the graph so that you can see the nodes without any additional information. We try to put semantics into the visualization. For example, different size, different colors, points that are closely together should have some semantic relationship, so they should also be semantically similar. And then you could identify different regions. And this is also a very active research area, how this deep learning and the whole big data wave can actually be useful in a sense that users and non-experts can look at it and make sense of it. And visualization is a core aspect in this context. With this, I want to thank you, and hopefully we get lots of interesting questions to discuss.
I'd like to invite the speakers back to the podium. Great, and I'll open the floor up for questions. I'm sure there are many. Yes? Do we have a mic? Yes.
Thank you. Thank you so very much for these very clear presentations of a very complicated matter from a humanities point of view. Maybe I will start with, or pick up something you said, Professor Meindl, at the beginning of your talk, which made a historical argument, which I, of course, very much like, because you mentioned the various steps or AI hypes starting in the 1950s, Dartmouth Conference, perceptrons being developed, the 1980s going on. Something you very eloquently did not mention or leave out at that moment, of course, were the negative side of this very optimistic development, the so-called AI winters. In your talk, of course, you gave a perspective, the challenges for the future, and this is what I actually want to ask. One of the challenges being energy for the current AI. Would you see any other factors right now, especially for this area we're talking about, so art and art history and image recognition, that might be not leading to an AI winter, but maybe complicate the story and the success story, which obviously is going on right now. I'm asking because, of course, from an art historical and humanities perspective, I see some challenges. One of the main challenges being training data sets, like the one you presented, the ImageNet training data, which in terms of Quellenkritik, we mentioned this morning earlier, so source criticism is highly a difficult training data set because we don't know where the images come from, if they have been trimmed, if they have been cropped, how they were enhanced. So everything what counts from an academic point of view, from an art historical point of view, is challenged with this. Also, it was mentioned we have to build our own training data sets that are somehow similar to the images, which is really a terrifying, in a way, terrifying perspective for art historians. So what might be the challenges from your perspective? And one thing I would like to pick up from this morning, the introduction of Elizabeth Gorayeb, you mentioned user friendliness, and which I would like to ask every one of you what might be the challenges for that, because you also talked about OCR being something like state of the art, no longer being a big challenge. And of course, I can take this to an archive, not being digitized, make my own photo, have it sent to my cloud, being OCR processed the same moment, and get it put into a Word document. So when will all this, what you presented now being a really, really challenging question for a future question, all this you presented be on my mobile phone?
You asked 100 questions.
I'm sorry, sorry.
And I can memorize only a few and start with a few, and then we perhaps can continue. With the dark side of AI, it was 20 minutes or something like that I had, and there are so much discussion, so I like to show a little bit what is behind that technique. If I understand that, then some of the discussions, for example, in the field of ethical use and problems around artificial intelligence become cumbersome. For example, there is the idea that one want to allow an AI algorithm only to work if one can follow what the algorithm did. If you see this is a request from people that do not know the techniques. No human can exactly explain how the way and the reasons to come to this judgment. And we asked that the machines can do. Then simple machines, the programmed machines, which was the first phase of computerization, digitalization, one can exactly say this is this method, and in this situation it does this, and then it does this. With these new learning approaches, there is not possible. So what is interesting in research, how you can influence something in the data set which is used for training to influence the later work of the algorithms working without training. And then there are some fancy effects, for example, recognizing traffic signs. So it works quite well. Almost all your cars can do this. But if with small post-its on such traffic signs, one can show to completely misteaching the algorithms that with some post-its, relatively small to compared to such a big sign, the algorithm come to a completely different decision what it is. So this shows that we are very in the beginning. So of course we all are fans because we see what's possible with computers. It's far away what humans do. It's very island concentrated. It is this image recognition. But we saw, or I showed that also the irony, at least now, cannot be detected. So I'm quite sure the next winter comes, because society every time looks for something else, and there's a while they are interested in it, and it's changing, but it will not delete this development. Then the development goes in the back, and if there are new successes, for example, in areas which are now difficult, I mentioned this with the networks to decide whether a network is from cybersecurity prospect a secure one or an insecure one. This decision today we cannot do because we have not training data, because we do not know the truth about a network. With the images it's easy to say it's a dog, and it's a frog, and this is this, and this is this. So we will see some development. There was one question from the many one I also like to say a few words. But perhaps you continue to try to answer the 97 question I left unanswered.
Maybe I can add a couple of words. Okay. one thing with deep learning is that deep learning is suitable only for a special set of questions and problems. As Professor Meinl already said, it's the perceptual questions. Image recognition, speech recognition, these are the things that can be answered, and everything beyond that is not really suitable to be solved with deep learning. And this is always the problem with these AI winters. People get excited, and then there are promises that cannot be kept, and then people are disappointed that it's not working out. But I think this deep learning, it's a big step. But it can only be applied to certain problems, and that's then another topic that you mentioned: training data. So this is very crucial. All these methods, they need lots of training data. There is lots of research that tries to look into so-called unsupervised learning, where you don't need annotated training data. And for example, the word embeddings that I briefly talked about, they don't need training data that is annotated because they only look at the context, and the context is the annotation. So they don't need humans to actually annotate the words. They take the words as they are in the text, and that's why they work so well. And the other deep learning methods only work well because there are millions of different training data. There's also a current research trend, something called one-shot learning or no-shot learning, where you actually try to learn with only one example. And what research are doing at the moment here is they try to see how children learn different concepts. They don't need 100,000 pictures of frogs to identify a frog. They need maybe one frog or maybe two, but that's it. And there is lots of research that tries to look in how humans learn and how computer can adapt this kind of style of learning, and really need only small examples to really then abstract enough and learn concepts. And this is probably the way to go. Unsupervised learning and this one-shot learning are very recent developments. So there is more to come. Unfortunately, I guess people will not start doing this in the art domain, but they will do this for self-driving cars and for other areas where you can make lots of money with it.
I'd like to address the portion of your question directed to me when I said that we're aiming for user friendliness. And I detect in the questioning of that principle a sense that all of this computer learning and application of AI to art history is unnecessarily complicated. And it's challenging a methodology that has been time-tested and could be shortchanged by some of these applications. And certainly there's an argument that can be made for that, for sure. With any type of technological development, there's going to be detriments to its application. But I'm approaching this as the director of an institute that was given hundreds of thousands of documents and millions of scans without any metadata. And the sheer volume of the project itself could be prohibitive. So I'm looking for help. And the idea that computer learning could possibly help out in figuring out what those images are is what I mean by user friendliness. But certainly, I think that it's very important to know that computer learning and advancements in technology are not a replacement for art history, but they're a complement to the study of art history. And they can very much be used for that purpose. Many art historians, I think, as soon as they hear about image recognition and image comparison, are ready to dismiss it because it casts to the wayside a connoisseurial approach. Yes, it does in its isolated state. It can also be used as an enhancement to that connoisseurial approach. Forensic analysis, by and large, is not very helpful to the art historian, but it is helpful in looking at the bigger picture. So does that answer your question? Or did I address your question? Yes, okay.
Thank you very much. I just wanted to challenge you to make clear what kind of concepts are we using. I think this became quite clear right now because it's the people dealing with huge amounts of data and archival records. So many people working in archives, museums, dealing with huge amounts of
certainly. Thank
Only
you.
a few words to the test set. When we do this research, we need a kind of benchmark to say, I developed this approach or this architecture or that, and then we want to globally compare what we do. So there is this composed set without the critics exactly what is it. It comes from different sources, not to give someone an advantage. And then it's accepted for a while as a benchmark, and every research group use it and experiments with this and shows these results, and then the publication you source shows I'm 5%, 3%, 10% better than the others. So the real sets, this, for example, with art sets, this is if these architectures are ripe to apply it to a special application area, for example, to medicine or to other things. So this is the early stage when we are in a competition, is like in sport, and to become a professor, you need to be the best accuracy. Professor Kressler made it. The young people here, our doctorants, they try, and I'm sure they will also make it. So in this sense, it's not. You should not look too much. What are the images? We need a 7 million set of images where we can fast use it, and where it is a reference, an international one, so that the competition is fair.
Yes. Oh, sorry. You, and then in the back. Thanks.
Yeah, Michael Müller from the Mosse Arch Research Initiative. I'm deeply impressed how far this has already developed, and the wide range of possibilities that you showed us. From a domain perspective, we now have a huge amount of solutions, and we can start to find the problems for these solutions. And I'm wondering if it's not, the time hasn't come now to start from the opposite direction and to get more in contact with the researchers in the domain and ask more thoroughly, what are your problems and where can we solve your problems with our technology? Because with, of course, you had to start with this tech-driven approach, but I see a great potential if for a slight change of perspective and a closer cooperation between this technological approach and the research questions, concrete researchers in the field, and not only in archives, but the people using archives to answer their research questions have. That I would like to hear what you think about this proposition.
Okay, I think I'm in the right place to answer this question, because I think I'm exactly in the middle between the two parties that you just mentioned. There is this, the large group of researchers that we have very close contact to, and we have been listening to their problems and their challenges for quite some time. And on the other side, I'm constantly sitting between my former colleagues that tell me about these, great improvements. So I definitely see the WPI as one of these institutions that have the potential to bridge this gap in a way that the communication between the domain experts and the IT personnel is established, and we have official cooperation projects where we are, looking at the individual problems that our researchers face on a day-to-day basis, and that starts with volume of information, that goes all the way to accuracy, creative aspects, that are very difficult to address by artificial intelligence. But I can assure you that we have a large spectrum of questions that we constantly try to discuss with the technical experts. And the other important thing here at the WPI is that we have the data and the resources to actually engage in active collaborations, because that's very rare. Training data has been discussed. So far, there is no data, at least, to start looking into adapting AI and ML algorithms for the art domain. So I can assure you that there is at least one organization that tries very heavily to establish a good communication between the two worlds.
Yes, Walter.
I found this extremely interesting, and I'm very thankful that you made the effort to tell us all this. I really am impressed. But I, of course, sit on a completely different boat. And my problem is, ever since 1993, when I signed a contract with John Rewald to finish his catalogue raisonné of Cézanne, I was supposed to decide on each picture by Cézanne if it's or if it is not. And that's how we met, Elizabeth.
That's right.
When you sent me photographs for Sotheby's to authenticate paintings or not authenticate. So my question is to you: is that painting by Gauguin that you showed, or is it not?
That's a very good question. I hope so, but I don't know. So it's just what I found online.
That's not your purpose.
That's right. That's not my job.
Yeah, but for me, it would be the main job for us.
But my job could be to assist you just in
Right.
your job, basically.
So we must find ways to work together in the future. You must be able to do authenticity as well, and I must be able to use your methods. That's the aim, I would say.
Yes.
I'm at an archive now, but I used to work a lot in research and teaching, and I'd like to enthusiastically support that. I do believe that there are many, many research questions that would be aided by this kind of technology, and it does exist. It's called digital humanities. It's been around for quite a while. And maybe not so much in Germany as present yet, as much as in other countries, such as the Netherlands, and maybe not in art history yet as much as in media studies, which deal more with popular media, like television, for example, or film even. But obviously, this is a kind of war between the two cultures, as they have been called. There's more the social sciences type of research, which has a greater affinity to quantitative methods. And of course, there's more the study of coming from literary studies, philology, that do textual analysis, which are only discovering this since recently. But at the moment, as some of you may know, there's this big initiative by the German Research Foundation and BMF, the NFDE program, which is funding to create a national research infrastructure of data, really, of data management and using data with quantitative methods and reusing data, so exactly, which would have great affinity to these kinds of methods. And there are also groups, and this is not just, this is also already for the traditional disciplines that use this every day already, such as the social sciences or medicine or the natural sciences, but there's also many people there from the humanities, and it's especially been people from music studies, and also art historians, I think also from Cologne. You probably know Holger Simon from Cologne, who's very active in promoting this. So there's a lot going on in this, and I think, and one of the main aims is actually to bring archives and IT and academia together to do this kind of collaborative research and to really learn from each other. And like Professor Storvik from RKD said, it just generates new ideas for new questions, new things that you've always wanted to do but have not been possible, just practically possible, you may now be able to do, but you can also generate new ideas and new questions. So I'm fully enthusiastic about this, but I also realize that there's a lot of difficulty because you really have to, you need collaborative work. It's not something that just one person can do. You need research teams, and it's also something that's not so established in the humanities. We mostly have people working as individual scholars in the humanities, so this kind of collaborative work and working in virtual environments across institutions and perhaps even countries is not so established, and this is also something I hope that this will promote, is really bringing us together from different disciplines and also across cultures and countries to work together.
I love that call to arms. Thank you for making it. I think we have time for one more question.
Okay, hello, this is Benjamin Gögge. I'm working on the cataloging tool for the WPI as well. And I wanted to get back to the question, is this Gauguin or not? And I think one important thing that maybe we need to discuss, if it is a possibility, to treat data not completely as binary. So that can occur to metadata, so that we can say, for example, that a specific specific date for an artwork is with a specific likeliness and accuracy correct or not. But also, for an artwork, we don't know exactly if it's a Gauguin, but we know it. We know that it was in these sources. And because of that, I think, it is important to open the sources and to make them available to the public and in the best way, and always in the best way for the person who owns the sources, so that they can decide what should be published and how it should be published, and allowing them to annotate it, which also is a part to help the person who at the end looks at the information to do their own interpretation of all these decisions that sometimes are transparent and sometimes are not. So the decision putting a work of art into the Gauguin catalog is, in the end, there are a lot of steps that are transparent, and there will always be a lot of steps that are intransparent. And using machine learning can help a lot, but also will cloud some decisions because you cannot look into the algorithm. You can just make some of the surroundings transparent so that you can see how was the algorithm written and how was it trained, but you cannot say, okay, this is the point where the algorithm went in this direction or that direction. Sorry for not posing a question.
Well, thank you. Thank you. I think we are out of time. Thank you, everyone, for coming today. And I hope this is the first of many such discussions that we can have on other places around the world. So thank you again for coming to this very groundbreaking event.
So that keeps me inviting you for the reception. So we are going down the hall, and there will be some drinks and some snacks, and you can continue your conversation with all the present speakers. Thank you so much.